Thank you very much. I have this really a great pleasure for me to be here in this beautiful city. And just to add a piece of information, I'm at the Institute of Advanced Studies as a philosopher of the residence. It's called the title. So, and thank you very much for inviting me to this talk. And this is not a logical talk. It's a talk in between machine learning and quantum field. But there are also behind some logical background, and I try to emphasize this point. So, the extensive research in the field of pattern recognition, machine learning, quantum computation, and information has inspired new ideas on some important general problems that arise in different disciplines. For example, logic, engineering, cognitive science, philosophies, and other disciplines. Why? We'll be seeing in that. Sorry. One of the core problems in these investigations can be described in a very simple way. How are abstract concepts formed, recognized, classified on the basis of some previous experience? And this, of course, is a difficult problem that is studied both for human and for artificial intelligence. The nature of concepts, as well the constraints that govern a general theory of concept, is and have been and continue to be a subject of much debate. For example, the position held by the Gestalt theory is very particularly illuminated in this regard. And this is a quotation compared to the holistic features, character of concept. So, from one side, we have machine learning. And what is machine learning? Can be maybe defined as a sort of art and science of making computers learn from data. And this is how to make computers learn from data, how to solve problems or recognize or classify new objects without being explicitly programmed to this aim. On the other side, we have quantum computing that describes information, quantum computing and information, that describe information processing with devices based on the laws of quantum theory. What is the connection between? Why this talk could be, my talk could be summarized as the result of a marriage. Okay, of marriage of not convinced, of a good marriage. From one side, machine learning, and from the other, computing. But why?
Hopefully not in that one sense.
Yeah. In the last decades, advances in quantum information computation science have received an increasing interest both in the computer scientists and in the data scientists communities. Well, the dramatic increase in the amount of data, as you can see here, is really a dramatic increase of the amount of data, especially unstructured data. This is the problem. This is structured data, and this is the light blue is the unstructured data, the big data. On the other side, we are faced with a dramatic theoretical speed up of computation by means of quantum algorithms, starting from the very famous algorithms by Shaw, the factorizations of prime numbers, which is the basis of cryptography, as you know. So now we have the notion of quantum supremacy. I don't like the term supremacy. I would say quantum advantage, let me say. Quantum supremacy, quantum advantage is a landmark, as Kresge say, the physicist, is a landmark goal in the field of quantum computing. represent the point at which a quantum computer can perform a calculation, a computation that is practical. This is practical, this is emphasized, practically impossible for classical computers to achieve. And the significance of achieving quantum advantage lies in its potential to revolutionize fields such as cryptography, material science, complex system simulations. And now we have also the reason, you see, the reasons of a marriage. We have the realization, the practical realization of the so-called near-term quantum computers. So quantum computer as there, not universal quantum computers in the sense that completely without noise. They are very noisy, but they are there. You can see the IBM Q computers, and this is a Google system, the Google Sycamore computers, and this is our I don't know what to say, Weizsäcker-Zentrum in Munich. And now we have in Munich a very good quantum computers with 20 qubits, ion trap quantum computers. So now, from one side, we have the standard techniques for extracting useful information from unstructured data, from big data, the so-called data mining, are faced with strong computational problems. We are at a sort of bottleneck. And you see also with the energy, for example, on the other side, the energy consumption, the so-called large linguistic models, GPT and so on, and Gemini and in artificial intelligence, has become a significant concern as the demand for more powerful and complex model increases. So training, but not only training, and also using large artificial intelligence models, especially deep learning networks, requires substantial computational resources, leading to a high energy use and a considerable carbon footprint. So, the main advantage of quantum computation is the possibility to drastically reduce time complexity, running time, and final energy consumption. So you see that it's clear now the results of the marriage. So the connection between machine learning and quantum computation is natural and inevitable in some sense. So, however, how can these fields connected? That is the problem. This is a question that quantum machine learning seeks to answer. Quantum machine learning. There is no universal definition of quantum machine learning. Field is really in infant stage, is in the early stages of development. Our approach is based. The main idea of our approach is increasing not the speed up of the computation, but the accuracy of classification. This is a so-called quantum-inspired machine learning, and this is exactly the way our line of investigation. Because there is a more philosophical assumption in this quantum-inspired machine learning, because it's based on general assumptions that common to other quantum-inspired fields, such as quantum cognitive sciences. And this is the assumption that some macro phenomena, not micro phenomena, macro phenomena, and process of the macro world can be described by means of the quantum format. This is the assumption underlies in our work. In our quantum-inspired machine learning approach, we develop quantum native classifiers. That is a classifier that are expressed in terms of the formal language of quantum theory, native. But these classifiers, these algorithms, can be run on classical computers. for example, of high processing computers, the HPC computer, despite this on the quantum formalism. So unlike the usual quantum machine learning approach, here the focus, I repeat, is on improving classification accuracy rather than speed up classification. But so our approach is currently classical device-based in the sense that we test our quantum algorithms on classical computers, for example, on high performing computers, the clusters, some clusters. But there is no reason a priori that prevents our quantum-like classifiers from running on quantum computers or near-term quantum computers, which are presently available, in order to have really good marriage, accuracy from our quantum-inspired classifier, plus speed up from quantum devices. So this is the reason of it. Accuracy and speed up from quantum computation. So, but this is not a dream, because there are recent results showing that our quantum-like classifier can be implemented on a quantum computer. And in the next future, I think in the next months, we'll try to test our quantum algorithms on quantum computers. Here you see a quantum circuits with 3 qubits, 1, 2, and 3. But so far, it's only they run on classical computers. So, what is a classical? Let us start from the basic notion of machine learning, of classification. A typical classification problem in supervised machine learning. Supervised machine learning there is, means that there is a training data set that which is supervised by a human. Okay, say that this is good. This is label 1, label 0, label 1, label 0, if the classification is binary. Unlike the ChatGPT model, which is the training is unsupervised. So in a typical classification problem, let me say binary, only positive and negative 0 and 1, we have a set of objects which belong to a given classification domain, for example, animal, and the classes, this is a very naive approach, the machine learning from a logical point of view, because it's purely extension. Classes are classes in a very naive set. And the classes, the object belong to, for instance, the classification domain might consist of the set of images of malignant or benign cells. Okay, this is the classification. Then one selects the features which is interested in, of course, properties, observable value that are supposed to characterize the object of the classification domain. For example, and then we associate to each object in class a feature sequence, a vector of number, the values of the observables you are interested in, and a label. The label stands for the class which the object is supposed to belong to. So we have, and then finally we have the notion, a pattern. What is a pattern? A pattern is a pair, which is an object vector that is a sequence, the vector of the features of the object, plus the label that classifies. And the training data set is the set of all the patterns. And classify, what does it mean classify? Classifying any possible unlabeled object of the classification domain into one of the classes we are interested in, assigns a label to a possible unlabeled object vectors. So you have an unlabeled vector, an unlabeled object, and then you classify 1 or 0, positive or negative. So the task of supervised machine learning, supervised classification, is to infer, tune, a function, a classifier from a given training data set. You learn the classifier, the machine learns from past experience, from the experience of the training data set, and then from a given training data set or a classification domain, assigns a label to an unseen and unlabeled object. So, for example, let us consider just a practical example. The domain, the classification domain consists of cats and dogs. The possible objects are cats and dogs. And so the set S is the set theoretical union of cats and dogs here. Then you decide that the features characterizing these objects are, for example, the weight and the height of the object. So you have an object vector consisting of a vector of Wx, Hx, the weight and the height of the object. Then you label the object as D or C, of course, stands for dog or cat. And so you have a pattern, finally a pattern, consisting of a vector and a label. And the set S training of all pattern is called the training data set. So you have a set of dogs and cats, you measure the height and the weight, you label it, and then you have the training data set. So your past experience, now how to classify new objects. So for example, you see here, our training data set, you have in blue are dogs and red are cats. Okay, it's in two-dimensional space. And you see, this is very well separated. Okay, but for example, there are some points here that are strange, that are quite strange, you see here. And so this is a training data set. And so the machine learning is based on a typical inductive reasoning process. From the analysis of experience, the patterns of training data sets, we derive a set of rules that contribute to the formation of the classification algorithm, the so-called classifier. So the classifier finally assigns a label, COD in our example, to each unlabeled, unclassified object vector. Formally, a classifier is simply a mathematical function from the Euclidean space RD, where D is the dimension of the vectors, into the set of the labels. There is no reason a priori why this should be a real and not a complex number, but using machine learning is taken to be, yeah.
Will it be a natural number, or do you need the reals for
Reals.
for continuity?
You need real numbers. Yeah. Oh, no, we should try, yes, to also, we can have also natural number, but in this way, you have to increase the dimensions of the vectors. You have to take of course, yeah. And so, and now the problem, how we test is an exam as at university or the school. How can determine whether our classifier has learned enough from the training data set? We create a test data set disjoint from the training data set, completely disjoint without time intersection. We apply the classifier to the set, to the new object, and we see the accuracy of the classification. So we see whether the behavior of the classifier is good or not, depending on the accuracy of the classification of the new object. For example, one of the simplest classifier, which is very, very simple but so powerful, is the so-called nearest centroid classifier. And this classifier relies upon the idea that the centroid of the object vectors of a given class, that we say the centroid of the dogs, represent a sort of gestaltic representative, an ideal prototype of the object of that corresponding class. So we know that the centroid does not reflect the real object. It's an ideal object. It's a sort of a prototype of dog and cat. And so you take the centroid of the dog plus the centroid of the cat, and then the classifier simply plus if the distance of the new object from the centroid plus is less than or equal to the distance of the new object to the centroid of the minus class. So what does it mean from an intuitive point of view? Whether the distance, whether the new object is more similar to a cat than a dog. This is the Euclidean distance, but you can use also the Manhattan distance or any other possible distance. So in this example, one builds up the centroids that are associated to the class of dogs and cats. So we have the prototypical dog, the prototypical cat, and an unknown object that is classified as a cat. If the Euclidean distance between the X and the prototypical cat is less than or equal to the Euclidean distance between X and the prototypical dog. So it's a measure of similarity. It's a measure, the distance is a measure of, is considered a measure of similarity. So here you see the prototypical dog, the centroid, the prototypical cat. For example, this is badly classified, it's wrongly classified, because this is really a dog, but the distance between from this point and the prototypical dog is less than this distance. So it's wrongly classified, and this is the accuracy. You count how many unlabeled objects are rightly classified, are wrongly classified. And you see, this is typical. This is the test data set, and this is classified is a linear function. You see, because this is a typical linear function. So you have a mixed-up training data set, then it is not a good classifier because it cuts the points into parts divided by a straight line. Okay? So, for example, in this case, the accuracy is a good accuracy, 94%. This nearest me classifier in this example. So it's good. It's good because they are so linearly separated in some sense. Yes, you see. Okay, now you see here, this is a tricky data set. You see, you have this banana data set because you have this banana here, then you have the blue one here, the blue one here, and the red one here, so that they are not linearly clearly separated. So in this case, our classical classifier has a poor. You need some more sophisticated algorithm, support vector machine, and so on and so on. You see, the predicted data is cut by a straight line. This is the result, which is bad. These are other classifiers. For example, you see these exceptional results of the neural network. This is a neural network classifier based on neural network, and the accuracy is terribly high. You see, it's almost the same. It's almost the same. It's more than 90%. And so now, okay, what is the idea now? This is a classical machine learning in a nutshell. Okay, just to give the idea. Now the problem, in order to use quantum computers, if we want to accelerate, to speed up the process, you need quantum objects. So the first thing we need is to transform if you want to classify classical objects by means of quantum computers, we had to magically transform classical data into quantum objects. Otherwise, you cannot program a quantum computer. So now we have, what is the idea? We have classical data consisting of observation from classical system, vectors, pure vectors. Then we have a quantum encoding. What is a quantum encoding? It's a function or is a set of possible function that transform objects of classical data into quantum objects. Sorry, but it's too hot. Into quantum object, in other terms, into pure quantum state. Vectors, what are pure quantum states, are vectors of length 1 in a complex space, in a Hilbert space, okay? Of length 1. This is the first option. Then we have a classification by means of classifying based on quantum theory, on quantum formulas. So, in details, we have an object vector classic. We transform, we encode X, a classical object, into a quantum state. I use the Dirac notation. You have a vector. This is the unit vector, and this is the projection associated to the unit vectors. In other words, the linear operator that project onto the line generated by X, okay? Which is a matrix, is a projection which is idempotent and self-adjoint. Okay? So the product of a quantum state by itself is the projection itself. Okay? So this is a projection operator in quantum state. So we have our classical cat by means of encoding. We have the quantum cat here, which is a projection operator. Of course, the same for our poor top cats on the right side. Of course, there is an infinite number of ways to encode a real vector into density operator, into a matrix, into a projection. And this is an open question. Sometimes the potential advantages of each option of encoding seems to be strictly data set dependent. So depends on the type, on the kind of data set you are faced with, you are interested. So, for example, there are, I don't want to go into details because it's quite boring. We use some stereographic projection or other kind of encoding, but it's not so interesting.
But maybe, let's say the choice is purely empirical, or do you have theoretical guidance?
We have theoretical guides. I would say heuristic guides more than theoretical. I would say for certain kinds of data sets, we see that, for example, the so-called stereographic encoding is much better than other encoding we know. Especially for example, for the example data set I presented before, dog and cats text, this is a kind of data set that requires the stereographic encoding. But this is a heuristic. It's an open question because so far the encoding we know, that I would say 90% the stereographic projection is better than the amplitude encoding, which is another kind. But this is only experimental. We tested with many, I think more than 1,000 data set of different kinds. But there is no theorem, or there is no, let me say, deep theoretical reason that justify the choice of one people. It's an open question. Yeah. So this is, for example, a kind of, this is a projection, is a matrix 3 by 3 is they are completely different. This is the stereographic encoding. This is the amplitude encoding. They are completely different projections. So now we have the classical data set. We encode the classical data set into the quantum data set, quantum data set. And what is a quantum data set? It's the set of all encoded classical objects with their own name. Very simple. But now we have the possibility to use a feature which is a quantum, it's a quantum feature to build up the so-called quantum centroid. Now, because now we have projections, pure states, okay? And what is now we take a move which is quite similar in the spirit to the classical as the nearest mean. We take the sample, say, here you have the encoded gets, and they are projections. Then you take the sum, which is weighted by the number of the cardinality of dots. This is not a pure state. This is a density operator, is a density operator, is a mixture. This means that is not idempotent. It's not idempotent. And this is something completely different. So you cannot represent the quantum centroid as a projection, as a line, just because it's a mixture. It's a mixture, is a density operators given by the sum, the weighted sum of the encoded object. So now, how to check again the problem? How to check whether a new unlabeled object is a dog or a cat by using a quantum encoding? Now we have quantum object, so we can use quantum mechanics, quantum theory. And this is physics coming into play, quantum physics, because we make use of a typical quantum feature that is a quite old problem, but still open in some parts. So how to distinguish is a problem of distinguishability of the matrix of the quantum centroid associated to the dots or the quantum centroid associated to the cats, because these are quantum states, mixture. So the problem is in general in physics, in quantum physics, how to distinguish experimentally two quantum states. You have two quantum systems you have a quantum system in two different quantum states. You have Alice and Bob. Okay, I am Charles. Okay, you are Alice. Sorry, I got Bob. Then I have this a particle. Just you know, I say, okay, I will send you a particle in one of these two states, rho C, rho T, or rho C, prepared in one of these two states, which are quantum mixtures. Okay. You have to find an observable that is self-adjoint operators. So you have to measure the quantum states, and then you have to guess whether the state that I gave you is rho D or rho C. Okay, this is the problem of the distinguishability, which, from a classical point of view, I would say doesn't make any sense, because they can be perfectly distinguished. They can be perfect. The problem is here that that there is no perfect way. Another term, there is no quantum observer such that Alice or Bob can as with probability 1, distinguish perfectly whether the state they received is rho D or rho C. Okay, this is it's a theorem. It's a theorem. So in our idea in machine learning is that instead of the relations, similarity relation based on the Euclidean distance, as in the near centroid, this similarity is replaced by, depends on the degree of physical distinguishability of quantum centroid. So our classifier, then we have a new measures of similarity that strongly depends on how similar are the two quantum states that represent the quantum prototypical tensor. And this is called the so-called Hellstrom discrimination of the state, because it was Hellstrom that proved that two states of a quantum physical system can be physically distinguished in a perfect way, if and only if they are orthogonal. So they are completely, which is a case which doesn't occur in nature, so to say, doesn't occur in nature. They are completely different and similar. So if a quantum physical system is prepared in one of the two non-orthogonal states, rho 1 and rho 2, there exists no observable, no physical quantity that allows to perfectly discriminate the states. However, Hellstrom proved, it's a beautiful theory, that rho 1 and rho 2 can be distinguished in an optimal way. Not perfect, but optimal way. And such optimal value is called Hellstrom bound. This is the best possibility to distinguish two non-orthogonals. And from a technical point of view, Hellstrom proved that there exists a dichotomic observable, depending, of course, on the state 1 and 2, whose possible eigenvalues, another term, possible values of the observables, gives rise to two projections, P1 and P2, that represent, respectively, from a logical point of view, the property being in the state rho 1 and B being in the state rho 2. And this is exactly what in the spirit we see opposite. So we have the two in our dog and cat, the quantum states, okay, the mixture. The Hellstrom observable gives rise to projections, PD and PC. And in the spirit of Birkhoff and von Neumann quantum logic, PC, the projections, represent the property in experimental proposition Birkhoff and von Neumann language terminology, the property being a cat, and PD represent the property being a dog. Because in Birkhoff and von Neumann considers projections as possible property, as mathematical representative of possible physical property. Okay, so now how to classify an unlabeled object? And this is now quantum mechanics. What is? You take the, since the probabilistic, is what is the similarity? The similarity, you take an unlabeled object, you encode this unlabeled object, then you take the two quantum, you encode the object, then you take the two projections representing the property being a dog and being a cat, you calculate the probability that the new state assigns to the property being a cat, and you take the probability that the new state, the new object assigns to the property being a dog, and of course you classify as a dog if the probability is greater than the probability, and so on. So it is very, so now finally you have the two states, the two quantum centroids representing the two quantum objects. You have the observable, the Hellstrom observable. You have the two projections representing the property being a cat, being a dog. You have an unlabeled object. You take the encoding, and the Hellstrom quantum classifier called say that X is a dog. If this is the Bond rules, the probability that X attributes assigns to P is greater than or equal to the probability the new object assigns to C, to the property cat. This is the we call Hellstrom quantum observer. Finally, we collapse into dog or cats. Okay, because we dequantize them. And what is the idea? The leading idea of this classifier is based on general assumption that is corroborated from an experimental point of view. That the higher is the Hellstrom bound, of the two quantum centroids, the better is the performance, is the accuracy of the classifier. In other terms, if you are able to distinguish in a very good way the two quantum states, the two quantum representatives, then you have a good classifier. So, in other terms, high distinguishability, highest bound, high distinguishability of the two states, high accuracy in the classification of a labeled object. This is empirical. I'm not able to prove a theory that there is a correlation, a functional correlation between the Hellstrom bound and the accuracy of the classifier. Says the more the higher is the Hellstrom bound, the higher is the accuracy. No, but empirically, you see, you have many data sets, different kinds. You have the blue part is the balanced accuracy, is the accuracy of the classification. And in the red part is the Hellstrom bound. And you see that there is an empirical strong correlation between the two quantities. The quantum quantity, the Hellstrom bound, and the classical statistical quantities of balanced accuracy. So this is in a nutshell the idea. I'll just to sum up. So you have a quantum training data set encoded. We have the positive and the negative class, dogs and cats. Then you have the two quantum centroid, and the Hellstrom classifier is again a function that assigns to every object, to a classical object, a label. This is completely similar to the nearest mean centroid. But what is different definition of the function, of course, which depends on the probability on the Bohr's rules in quantum mechanics. And there is another important quantum features in classical learning, machine learning. Additional copies of one of the same object are completely useless because they do not carry new information. If you have a copy of the same object, in other terms, more copies is equivalent to one. This is completely different in our case in quantum mechanics and in quantum in our Hessel classifier, it is strongly depends on the number of copies we take into account. So additional copies of one of the same object state are very useful because they, this is a completely quantum feature, they do carry new information. More copies are better than one, but you understand the reason why from a physical point of view, because since the two quantum states cannot be perfectly distinguished, is you repeat, if you have a copy, more copy of the same physical object, you increase the Hesson bound. And this is the physical reason, And the idea is to harness this feature to enhance the accuracy of the classification. There is of course a price you have to pay, because taking more copies means more computational resources you need. You need more computational resources because you have an exponential increase in the complexity of the computation. Because this is a tensor product. But from the point of view of the accuracy, for example, let me see. This is the first time we train our banana, which is difficult. You see the banana, as I mentioned, and this is what the result with the copy. And we were really very angry. You see, completely. So this is the conclusion. What our classifier is terrible. It's terrible. It's worse than the classical one, the nearest. But you see, increasing the number of copies. Here, this is the classification with 6 copies of the objects. And this is something very similar to what happens with the neural networks. It's a very good classification. So the number of copies is small. Yes.
And copies in which sense? So you take the same test data and just run them 6 times instead?
No, I take an object, a classical object, I encode the object, this is a quantum state, and I take the n-tensor product of the object. And I have again a quantum object, because the tensor product of the same state is a quantum object. Then I apply the same ingredients of the classifications. I take the Hellstrom bound of the quantum, the n-tensor product quantum centroid, and so on and so on. So this is the reason why it's very demanding from a computational point of view, because you don't repeat the experiment with one copy. You take a system which is the tensor product of the same object. So it's a big Hilbert space. It's a big Hilbert space. But you see very good classification. You see the accuracy. For example, the banana. And you see also the Hellstrom bound in the other column. With one copy, low distinguishability of the quantum centroid, low accuracy. And then we have an increasing, progressive increasing, so both of the Hellstrom bound and the accuracy. At the end, with 6 copies, with 7 copies, our computers fail down. Also, the computer of the Leibniz Center, we have not able more than 6 copies. But I suppose that after a certain, I'd like to prove that after a certain number of copies, there is a sort of plateau. And so it's not, there is a number of copies, an optimal number of copies. But anyway, you see, with 6 copies, we have a very good distinguishability of the 2 quantum states and a very good accuracy for the banana data set, which is very mixed up, you see. And so, you see here, but not only accuracy, other statistical figure of merits in statistics are open. The infidelity, the F1 score, which is used machine learning. you see the red one is a Hellstrom bound, and there is a correlation. What I don't know, what we are not, which I'm not able to characterize in a mathematical way, but it's empirical. So far, it's empirical. It's empirical. And okay, we tested our classifier with 12 different. We contrast this classifier with 12 different standard and very good, very well performing classifiers, neural networks, and so on. And with the Hellstrom classifier on 40 different standard data set from a well-known repository of data set, the machine learning benchmark. And we took balance accuracy as a scoring parameter for the comparison. And so, just for curiosity, discriminant analysis classifier, support vector machine classifier, nearest neighbors, linear classifier, any kind, neural network, multi-layer perceptron, many classifier. This is the balance. The more blue, the better is the accuracy. The more blue. Red is better. This better accuracy is in here. And you say the quantum classifier, you contrast the performance of the quantum classifier and in this picture, and you see here, this is the average success rate with this data set. As you, the Hellstrom classifier has an average success rate of 73%, which is very high. Much higher than the multi-layer perceptron, which is neural network, reinforced neural networks. We applied also this classifier to evaluation, to the so-called chronogenic assay evaluation, which is a biomedical imaging. In chronogenic assay evaluation, to identify the most discriminant feature allows us to enhance the cell colony segmentation. This is what does it mean? The problem here, you have a colony of here of cells. They are treated based of chemotherapical cell malignant cells. Okay, they're treated with some chemotherapical drugs. Then the cells tend to group into colonies, into different colonies. There is no, it seems to be unbelievable, there is no mechanical way to count the colonies. So they have to be counted by hand. And so the problem was to identify what is the most discriminant feature allowed to enhance the colony, the cell colony segmentation. And we found that the so-called homogeneity of the pictures is the most discriminant features for the segmentation of the colony, and this was proved. And this the Hellstrom classifiers was the best classifier for this task. For example, much better than the neural network. So, in other terms, these classifiers do not be a novel and outstanding methodology compared to conventional machine learning classifiers. I cannot say it's the best because in machine learning there is the so-called no free lunch theorem. So say that there is you cannot say that there is a best classify for every kind of data set. So, and now, which are the open plots that the further developments? First of all, as Rand says, for a given class of data set, find the best encoding and the optimal number of copies. This is a theoretical. Find, if any, a scoring, a statistical figure of merit that is analytically correlated to the Hellstrom bound. In other terms, so find in an analytic way statistical like balance accuracy if one goes over or a mixture of these figure of merit. And then we generalize, this is also generalized to multi-class classification, because this is binary. It's binary classification. What happens if there are more than two classes? From a classical point of view, it's not a big problem. It's not very challenging. But from a quantum mechanical point of view, it's very challenging, because so far now there is no generalization of the Hellstrom theory to a number of states greater than 2. No, there is no theoretical result. There are many investigations of this problem, because it's a physical problem, but there is no algorithm, there is no theorem, say, that finds the optimal value of the distinguishability when you have more than 2 states. So there is a suboptimal, and we use the suboptimal procedure to extend this classifier to more than 2 classes. And the last but not least, the problem, what I have the problem in my heart is test this classifier on near-term quantum computers, which is realistic, because now we have near-term noisy quantum computers. So far, we are able to implement the Hellstrom measure circuit on IBM quantum computer and to prepare the encodings of the test data set on this device. Once that this classifier is trained, so the training part is classified. And that's the point. What we expected is highly desired to have the training part based also on the quantum computer. It's not about it. So in this way, if we are able to find, so now what is the situation? We train the data set, and this is a cluster of computers. So the training is classic. The classification, the testing is quantum. Okay. What is missing to close the circle? What is missing is a quantum algorithm for the computation of the Hellstrom bound here, to calculate Hellstrom bound here. So, in other terms, what we have to have is train the data set, not here, but here. So find an algorithm, a quantum algorithm, to find the Hellstrom bound. And if we're able to do that, then we have every step of the classification problem is quantum. And this way, we turn to the marriage. We have accuracy based on the Hellstrom classifier, plus speed up based on quantum computers. So, in order to close this circle. Yeah, and I would say that this, just to finish my talk, sorry, I took too much time. I'm sorry. I'm sorry. You should stop me. So the conclusion also, more general conclusion. By bridging the gaps between these seemingly disparate disciplines, you see, there are concepts coming from physics, from machine learning, from computer science, from logic, and so on, from philosophy. The quantum-inspired machine learning approach can lead to methodological advancements, foundational implications, and also innovative applications. Innovative, why? From a methodological point of view, by putting together concepts from quantum mechanics, information theory, pattern recognition, epistemology, and logic, because there are some very, there are many epistemological aspects behind all these constructions, which are quite rough, so to say, from a philosophical, I repeat, from a philosophical point of view. The same concept of class. An interdisciplinary approach to quantum pattern recognition can provide new insights and overcome limitation in existing approaches, which are philosophically rough, I repeat. So the use of quantum concepts could open new avenue for designing algorithms that are more robust to noise and uncertainty. This is from a more methodological, but also from a foundation point of view. Quantum theory, we know, is the nature of quantum theories is inherent, intrinsically probabilistic. And its ability in an extraordinary way to deal with uncertainty suggests that it could provide a more fundamental understanding of machine learning, where uncertainty in classical machine learning is reduced, so to say, to classical concepts, which are not, by definition, very good, but they do not match real certainty by this. So quantum concept as superposition, entanglement, non-locality could lead to a deeper understanding of the underlying principle of machine learning and how they relate also to human perception and cognition. And this is the part of so-called quantum cognitive sciences. And then from applicative impacts, you see, the potential application of quantum pattern recognition are immense, are vast. Quantum enhanced pattern recognition algorithms could lead to improved object detection, object classification, more accurate diagnostic tools, a more effective language processing system. There could be also an impact on the large language models, which are essentially neural networks, very sophisticated layers of neural networks. And this advancement would have significant societal impacts, also in fields as medicine, security, communication, and sustainable economy. Just because quantum computers are not so terribly, we say, eater of energy like classical computers. I mean, from a theoretical point of view. And so, thank you for your attention, and I apologize for my long talk.